Hello and welcome to my video, lesson 1.3 on the domain for a composite function. So when considering a domain, we need to consider what the restrictions are at the different stages of the composite function. And depending on what we're doing, those stages can look a little different. The order of them might matter. So the composite function that we're normally going to look at is when we're talking about like f of g of x, like it shows here. But we could also see like f over g, in which case, you can imagine that whatever is on the denominator is going to be restricting as well. So we're going to look at both of those sorts of things today, the general idea of domain of a composite function. So consider the functions here for question 1, f of x and g of x. What is the domain of these composite functions? So we have an a function and a b function. So this is f of g of x and then g of f of x. So for the answer for a, I really want to take our time here and remember that it's f of g of x. And g of x is what? Well, g of x is 1 over x plus 2, which means that whatever you put in, so if it's a function of a function, whatever function is inside the other function, in this case g of x, is going to give us one of the restrictions or part of the restriction. So right here, we can say that x cannot equal 2. Okay, we can continue this now and see if there are any other different restrictions. I don't think there's going to be in this question, but we could. So, and some questions there might be different restrictions. So we substitute that in for our x, and then we expand and simplify. So this is going to be x squared plus 4x plus 4 minus 4. Which really means that it's just going to be like this. Oh, if it's multiplying top and bottom, it's going to have a minus 4 minus 16. Minus 16 plus 1, so plus 15. There you go. And you'll hopefully see that the only restrictions would be from the denominator, and it'd be the same restrictions that we had before because it's just x plus 2 times x plus 2. So our restriction is x cannot equal 2, where x is in the real numbers. So we're always going to have x in the real numbers, but in this case where x cannot equal 2. Okay, let's look at it the other way around and see if there's anything different. So it'll be g of f of x, and so it's g of x squared minus 4. But that doesn't really change anything, so we're good to go. Then when we put that in, it's going to be x squared minus 4 plus 2. So when we simplify it, it's x squared minus 2. Now, unfortunately, that's not a very helpful restriction. If I had thought about it a little bit more ahead of time, I could have made that a plus 3 or something to make this more clear. But basically, our restriction is still going to be based off this denominator. We're always going to look at the denominator. So in this case, the restriction is going to be, again, that may be a little bit less clear, but it is a difference of squares. It's just not a square. It's we'd have to square root it. So we're going to have that on the denominator, and so x cannot equal plus or minus root 2. So this does work. It's just not a normal number. If I had spent a little bit more time thinking about this ahead of time. And on a test, I probably would. I would make this a 3 so that this turns into an x squared minus 1 so that it factors out nicely. But it's the same idea. All right, let's continue on. Consider the functions f of x and g of x below. What is the domain? So it's the same question. We're going to do this again and again. We're going to have 3 different versions. I recommend you pause the video now and try it out yourself and see how it looks. Okay, so this is f of g of x. Well, g of x is tan x. And before we continue, let's look a little bit more carefully at tan x. So f of sine x over cos x. So this is what tan x is. And if this is true, which we know it is, then cos x cannot equal 0. Now this question is not 100% clear for talking radians or degrees, but we've talked about it before. By default, radians is the better answer. So if we rearrange this, x cannot equal, and this is when cos is 0. So that's when x is 0. So that's the straight up and straight down position. So it's pi over 2 and 3 pi over 2. So those two values are values that x cannot equal. Then what we have to do is we have to plug that into our f of x function. So we then go into here and we say, well, that is our value inside the log function. Well, what's the rule for logs? Log x must be greater than or equal to 0, right? Or the x inside the log x. Maybe I'll write it like this. Because it's log base of the answer equals the exponent. Well, there's no way of having a base 10 and then having an exponent and then somehow getting a negative result. It's just not possible. So therefore, the inside must be greater than 0. Greater than or equal to 0. I'm going to maybe use a different letter, log y. So that means that sine x over cos x must be greater than 0. Well, hold on a moment here, because this means we have to restrict our function such that this results in a positive value that doesn't equal 0. So first of all, can't it must be greater than 0. Can't even equal 0. Yeah, so that means that sine x must also be greater than 0, and tan x must be greater than 0. Well, where does this happen? That happens in certain parts of our unit circle. So if you think about cast rule, right, tan and sine must be positive. Well, that only happens here, only in one spot. I guess no, that's not a fair statement. Sine x cannot equal 0, and tan must be greater than 0. So it's in these two spots. So x cannot equal where sine x equals 0, so that's 0 and pi, and like 2 pi, etc., dot, dot, dot. But also, because of the tan statement, x is greater than 0 and less than pi, pi over 2. And then also greater than pi and less than 3 pi. And actually, this is enough of a restriction for the whole question because these are satisfied and these are satisfied. So you can see that these composite functions can get really wild if we add logs or trig inside of them. Let's go ahead and do this in reverse. So what if we did g of f of x? So this will be g of, and then f of x was the log x function. Well, like we said before, log x tells us that x must be greater than 0. Okay, so just straight up we have a restriction there. But when we put it into the g of x function, remember that this is tan x, so it's tan of log x. And we know that tan x is really just sine x over cos x. So that means that cos log x cannot equal 0. Whew. All right. So if we want this to not equal 0, we have to solve for x here. So what we can say is looking inside the cos function, log x cannot equal when does the cos function equal 0? Well, I guess it's at these two locations, just like the last question. Dot, 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 dot. And then if we wanted to solve for that, going in reverse, I guess, that's the answer. So it'd be base this to the exponent this. Base this to the exponent this. Dot, 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 dot. So this is a restriction and this is a restriction. So whatever's on the inside always restricts the question, and the final result also restricts the question. So you need to look at both parts and see if there's anything there that restricts. You can kind of see the idea that the red one kind of restricts the green first and then an additional restriction. And the blue one restricts the pink one first and then an additional restriction. Okay, let's go on to the next question. All right, I recommend you pause the video now and try this yourself and see if you get the same answer that I do. All right, here we have, we're going to start off with a function within a function question. And here we have f of x, but instead of the x, we've got g of x. So we're going to put in the square root x plus 1, which means that x must be greater than or equal to -1. Otherwise, the square root function will be imaginary. And so this is an important thing to notice here because you have to find those restrictions during the process of creating the function. Otherwise, you might miss some of the restrictions. And I think you'll see it on this version of it. Because when we put this in, to the above function, whoops, that's not squared, that's to the 4 minus 2, and then we have square root x plus 1 squared. When we put this in, I hope you can see that this is actually going to expand out and cancel a little bit. So we're going to get x plus 1 squared minus 2, and then this is going to cancel, and x plus 1 like that. And so as you go here, you can see that there's actually not going to be any restriction later on. And so the restriction that existed prior is even more vital than it seemed to be before. So now it's going to be, oh wow, this is a beautiful question. It cancels out very nicely. And so this is going to be x plus 1, x minus 1. Okay, and so what you can tell here is that even though the final answer seemed to make it that there's no restriction, it just seemed to be a normal quadratic, here we know that there is a restriction. And so this is going to show up when we graph this. And this is kind of like honestly, some of the most shocking or weird kind of questions, because the numbers aren't there and yet they still have an effect. Or the numbers aren't there anymore, I should say. And it's because when you cancel, you have to add those restrictions. It's as simple as that. Okay, and so like we saw before, we can write this different ways, but I'm going to do y1 of, and for some reason your calculator allows this, so this should work nicely. So there's our one function, and there's our other function, and you can see that the pink one, even though if we were to graph, we can do this right now, if we were to graph the x squared minus, minus 1 function that we simplified to, you're going to see it looks the same as the pink one, but it doesn't have that same restriction, right? So it doesn't have that same restriction. So the green and the pink look identical. As you can see, it's like 0, -1, 0, 3, 8, 15, 24, except the pink has this error, and it's because of the function within a function statement. So I'll get rid of the green one more time so you can see what that looks like. Okay, let's keep going and do this in reverse here. So we've got the same question, but we're doing the two functions reversed from each other. So inside the g of x function, there's no restriction. Like these are normal. But once we plug it in, let's see if there's any restriction. So now we're going to put in x to the 4 minus 2x squared plus 1. And inside that function, we cannot have a value that is less than 0. It has to be positive, right? So that means down here that x to the 4 minus this plus 1 must be greater than or equal to 0. Okay. Well, let's restrict it and see what happens. So this is going to be x squared minus 1 minus 1. Oh, that's fun. That's a kind of a fun expansion here that we're seeing. We normally don't see expansions this exciting. plus 1, x minus 1, x plus 1, x minus 1, and that result must be all greater than 0. So if we want it to be equal to 0, we would say like x equals positive or negative 1. So we can tell that those are kind of the boundaries. And so what we can do is pick a point in between them and pick a point outside of them and see what happens. Now, I know since it's expanding upwards, I'm guessing the points in between them is going to be the problem. So let's pick a point. Let's pick 0. No, that'll be fine. Let's pick a point outside of it. Let's say 2. No, I think that'll be fine as well. Okay, let's graph it and see. Yeah, it touches but never crosses. So we're actually fine. So interestingly, this restriction eventually has no impact. And because of all the stuff that we just did, you can see that like the factoring was actually useful here. It ended up being x squared minus 1 squared, then square rooted. And so those two things can cancel. And it looks like this. Well, that's just half of the factoring that we did before. And so this is what our final answer is going to look like. But there's actually going to be no restriction on it. The only restriction is the standard restriction of x is in the real numbers. Okay, kind of interesting set of questions. Let's go ahead and try another level. So the next one is f of x over g of x. So how's this going to look? Well, not going to be too crazy. The only things that you have to know is a denominator cannot equal 0. There's no simplifying that can really happen here. So the denominator cannot equal 0, right? And if there's other restrictions, you also follow those. So in this case, because the denominator here is a radical, so the radical tells us we can't have a negative inside of a radical. So x must be greater than or equal to negative 1. And since this cannot equal 0, x cannot equal negative 1. So if we combine these two ideas together, then we can say, well, x must be greater than negative 1. And that is our new domain. Okay, last but not least, we're going to do this but in reverse. So g of x over f of x. So there's our first step. So just like before, the restriction on that radical, doesn't matter if it's on the numerator or the denominator, x must be greater than or equal to negative 1, still holds true. Then we can look at the denominator and we can say, well, this cannot equal 0. So what values can it not be? Well, if we factor this a little bit, we can get it to look like this. So this part here tells us that x cannot equal 0. And this part here, unfortunately, is a little bit more annoying, but x squared minus 2 cannot equal 0. So if we rearrange that, x squared cannot equal 2. And so when we square root it, x cannot equal positive or negative 2. Okay, so we have these three different restrictions. We want to write them kind of all together if possible. Okay, the only ones that simplify together are the, since x has to be greater than -1, you don't need to say this part, right? This is already included inside this restriction. So we're not going to include that part because we don't want to, like, as mathematicians, we're really lazy. We don't want to write things twice if we don't have to. And so if we write this all together, we would say that x cannot equal 0, x cannot equal 2, and x must be greater than or equal to -1. And this is our final restriction. Oh yeah, and obviously, as always, x is in the real numbers. So every question is a little different, and you can look at it when we're talking about these division statements. You can look at it for a function within a function, and you just have to look at it for any given stage of your question. Is there a restriction on that stage? And then follow it along, and that's it. So I hope this video helped you better understand the domains for composite functions, and good luck.